So, buddy, how long have you worked as steward?
A little over 26 years.
Wow, so it's almost the same as me.
I know, I never thought I'd be anywhere for that long.
And neither did I, but you know, we have all these big telescopes and it's kind of makes it hard to see the grass being greener anywhere else. Probably the same for you.
That's true. Well, there's no place else where I could work on big telescopes like this.
Yeah. So how would you describe your job?
Oh, wow. It's an interesting mix of research, development, and production, just like a shop floor.
Mm-hmm.
In the end, our job is to turn these mirrors out for, in as little time and for as little money as possible. But we're doing something, in most cases, that's never been done before. So it requires a certain amount of R&D just to accomplish that.
So each one, especially each time you go up in scale, I'm sure it's a new adventure.
Yeah, that's right. That's been dramatically true. I mean, we've done so much better whenever we make something for the second time, but there haven't been too many opportunities to do that.
And I presume there's a whole set of experiential engineering that gets embedded in your head as you go through these projects, because the challenges are very unusual.
They are. I mean, I'm not sure what you mean by experiential engineering.
Well, I mean, it's nothing's been written in a book, right? There's no book to look up for any of this stuff.
That's right. Yeah, for just for certain very basic operations. But as soon as we've gotten into mirrors, bigger mirrors, or mirrors with shorter focal lengths than have been made before, or extreme off-axis mirrors, we're in virgin territory and need to figure out how to do things.
So let's get a sense of how how good an astronomical mirror has to be, and how good the mirrors that come out of the Mirror Lab are. I mean, give me a sense of the quality of these pieces of glass.
Okay, so if we had to come up with a single number to characterize the accuracy, we'd say 25 nanometers, which is almost exactly a millionth of an inch. That would be the average error. But, of course, I don't have much of a concept of a nanometer. It's a mathematical thing to me.
Mm-hmm.
So to try to put it in more human terms, if one of these mirrors were expanded to the size of North America, from the Atlantic to the Pacific, then the highest bump would be about an inch high. Wow.
That's amazing.
Yeah.
Now, why do they have to be that good, though?
Well, you astronomers have come up with these requirements. It has to be accurate to a small fraction of a wavelength of light in order to avoid distorting the images relative to what a perfect mirror would make. Mm-hmm. And once it's as accurate as a small fraction, say a 20th of a wavelength of light, you don't gain much by making it better. The images can't get significantly better. So that's the threshold. The mirrors are not perfect. We make them good enough. We keep working on them till they're at about that level, 25 nanometers.
And when you're talking about imperfections or errors, this is just the roughness on a scale of inches, or the whole thing, the whole span, 27 feet of it?
Yeah, it is a little bit more complicated than something you can characterize with a single number. On the scale of the whole mirror, you can get by with an accuracy of around 100 nanometers, and on scales of say a foot, it needs to be about 25 nanometers, and on inches a little bit better, maybe 10 nanometers accuracy. And the reason is that for any ground-based telescope, you have to do better than the atmosphere.
Right.
And the atmosphere distorts the wavefront quite a lot on large scales, very little on small scales. So the mirror has to have an accuracy with a similar spectrum or distribution of errors.
So presumption in this extreme spec on the mirror is that you're going to be correcting for the atmosphere as well. When you use it, you're not just going to be dealing with what the atmosphere gives you. I mean, in a sense, they're designed to work at close to their diffraction limit, or
that's right. Yeah, with an adaptive optic system that'll correct for the atmosphere, we don't want the mirror putting any additional errors that are not corrected, so that yes, it will be nearly diffraction limited over the full 8-meter size of the mirror, or in the case of of GMT over the 25-meter size of the whole telescope.
Yeah. So what does what do you start with? I mean, when you crack the lid on the oven and on a big mirror, how good is it already?
Okay, well, let's go back a little bit more. What do we really start with? We make these mirrors from scratch. We get blocks of glass from a glass company and melt them in this mold that gives it the honeycomb sandwich structure, which is a great mechanical structure for a telescope mirror. And it gives it all the mechanical properties we want. But at that point, it's only accurate to a couple of millimeters. It's nowhere near optical quality. As you know, we spin cast the mirrors, so we produce roughly the right parabolic shape during the casting, but that has nothing to do with optical quality. That's just so we don't have to grind out lots of glass to get the overall curvature.
Right. So in precision terms, you're factors of hundreds of thousands or millions away from where you need to be.
I think it's around 100,000. Right, going from say 2 millimeters to 20 nanometers. That accuracy comes in stages. We go through 5 or 6 different stages of improving the accuracy, and initially just getting rid of some extra glass, because we always cast a little bit extra in case there's a problem during the casting. So we have to get through maybe 5 or 10 millimeters of extra glass, and in the process get down to an accuracy of say 10 microns, and then machine it down to, the machining would be good to that level. And then we start the lapping processes, which are more precise. You have much better control of the shape of the mirror when you start lapping. And that goes through a number of different grades and eventually gets down to this accuracy of around 25 nanometers. And the process polishes the mirror, makes it shiny or microscopic smooth on a microscopic scale.
So just backing up to the first stage, what do the machines that do that first job look like? I mean, they're just literally abrading, grinding the surface?
Okay.
And how?
All right, so the first job, I think we're talking about the machining or the generating. And that's just like the machine is a big lathe, just like you would use to cut metal. And the process is the same, although the tools are designed to cut glass rather than metal. But you've got a tool on a spindle that moves very slowly from the outer edge of the mirror to the center, while the mirror rotates slowly under it. So the tool executes a tight spiral pattern all the way from the outside to the center of the glass. And it just removes anything in its way. So the accuracy you get is determined entirely by how accurately you can move that tool. And on a big machine like this is about 9 meter bridge, we can get an accuracy of around 10 microns. And I don't think anybody does much better.
That's pretty amazing.
Yeah, on a machine that size. But again, at 10 microns, you're still 3 orders of magnitude away from where you need to be for a finished telescope mirror. So that's when you go to these lapping processes, where the tool is now a disc instead of a spinning wheel with diamond particles in it. And you don't try to control the position of the tool. You just rest it on the surface and rub it around on the surface with a certain speed and with a certain force, downward force. So the faster you rub it, the faster you take off the glass, and the harder you press, the harder you take off glass. But none of this depends on the accuracy of positioning the tool, and that's why you can get to much better accuracy on the surface. Your accuracy is limited by a number of things. One is how well you can measure the surface, but another is the resolution with which you can remove glass. Smoothing a surface, controlling the shape of it is primarily a matter of removing glass from the right places. We never add glass to the surface. So we have to identify the high spots and
Which
wear
Which
them
leads
down.
to
Yeah.
these horrible mental images of having a table where you keep shaving the legs, and you always have one leg shorter than the other, so you keep shaving, and
Right.
so you have to converge. That
Yeah, and there's a little bit of that. I mean, we never remove exactly the right amount off of exactly the right places, but we do make it better almost every time. And yeah, like the guy shaving the legs of the table, we go through 50 to 75 cycles of polishing and measuring
wow.
before we reach that final accuracy.
And one question that I'm sure there's no danger in that sense, but there must be a lot of mechanical stresses on the mirror itself by the process. I mean, glass is not a solid, so I presume the glass accommodates that. There's never any concern about shattering or breaking
Oh,
an
well,
actual
no,
mirror.
I wouldn't say there's no concern about that. I mean,
Yeah.
we worry about that a lot in almost every stage of the process. And one does get some fractures in a big mirror.
Mm-hmm.
And as long as they're identified and they're small and they're treated, they're not going to cause any problems. But I don't think anybody's ever produced an 8-meter class mirror that doesn't have a few flaws in it, a few fractures.
So
that have
these
to be
are
treated.
small scale propagating fractures
Yeah.
through the whole substrate or just on the surface?
No, just on the surface, right? And that's the important thing. They've got to be kept close to the surface, and there's a certain depth on the order of a millimeter at which a fracture will not propagate during the life of a telescope. Now we try to identify things that are a whole lot shallower than that and treat them. But you know, it is a concern at every stage in the process. In the casting, where there are very high stresses on the glass as it's cooling, and when you lift it and it still has a mold attached to it.
Mm-hmm.
So sometimes there are fractures that occur then and have to be treated. And while we're machining, I mean, the machining process itself is a matter of just putting microscopic fractures all over the whole surface. That's how you that's how you remove the glass. And we have to inspect it and make sure we haven't accidentally put in some that are too deep. And sometimes we do find little flaws like that and have to grind them out by hand.
Mm-hmm. Now, the mirror, when it's in the telescope, is going to be subject to another set of forces and stresses, so it doesn't keep the pristine shape it has sitting there in the mirror cell, presumably.
Right.
So there's a whole nother level of adjustment.
Well, yeah, and you're getting to one of the reasons that big mirrors are made out of glass. I mean, of course, you have to remember that it's mostly a coincidence that we use the same material for mirrors as for lenses. And we don't care about the optical properties of the glass. The light never goes through it. The sole purpose of this mirror is to hold a layer of aluminum that's 1,000 atoms thick in the right shape. But one reason we're able to do that is that glass is perfectly elastic, meaning that if you bend it and then release the bending stresses, it'll come back to exactly the shape it had before. And that's a principle that we use in making the mirrors and getting them to work in the telescope. When we measure a mirror in the lab and show that it has this 25 nanometer accuracy, it's supported on a precise set of actuators. For a big mirror, it's about 160 actuators that are at certain points under the mirror, and that all of which have certain forces. And then, as you say, when it gets shipped to the telescope, it's not in this perfect support configuration. It's just some safe way of handling it to get it to the telescope. But it'll bend by many microns on the transport support. And then when it goes into the telescope support system duplicates the supports we had in the lab and we measured it. It's really the other way around. The telescope support is the defining system, and we duplicate that in the lab. But anyway, when the mirror is installed in the telescope, the same set of support forces are reproduced, and the mirror comes back to exactly the same shape it had in the lab, limited only by the accuracy with which you can reproduce the forces.
Mm-hmm.
In principle, it would come back to exactly the same shape.
Right.
And other materials don't do that. Metals.
So in a trade-off, you could imagine light and very rigid materials, they might be brittle, I suppose. So glass, if you look at all the possible materials you could make a large reflecting surface off, glass just still wins?
It still wins. Now the other reason which it shares with lenses is that it's polishable. Mm-hmm. It's fairly easy to get this microscopic smoothness mm-hmm. that reflects almost all of the light. And once it's aluminized, it reflects about 90% of the light. Mm-hmm. And with lenses, you don't want to reflect, but you don't want it scattering, so you need that microscopic smoothness. And glass has that.
And we say glass. I mean, is it fancy glass? Is it regular glass? Is it special in any way?
Well, what we use at least is real glass. Some telescope mirrors have been made out of glass ceramics that are a mix mm-hmm. of glass and crystal, but ours is pure glass, meaning it doesn't have any crystalline structure. It's amorphous. And it's chemically the same as Pyrex cookware, mm-hmm. called borosilicate glass. We get it from a different company, O'Hara, rather than Corning, who makes Pyrex. Right. But chemically it's the same thing. It's a very pure and uniform form of borosilicate. Mm-hmm. The properties don't vary across the batch or across the mirror. But there's nothing terribly fancy about it. Right. And we use it for the same reason it's used in cookware, that it doesn't expand very much when the temperature changes. Mm-hmm. Just, soda bottle glass, you wouldn't be able to use in a telescope, and you wouldn't be able to put it on your stove either, because it would break when it expands with the temperature.
Or window glass, same
thing. Right.
So, having made these almost perfect mirrors, there is still a set of challenges involved in delivering that performance, in a real telescope. What are the biggest challenges actually to delivering that perfect, spec that you had on the mirror when you took it off the polishing machine? Well,
there's several things. I mean, one is to maintain the right forces to support it, and another is to keep the temperature uniform, because even though this borosilicate glass is very good, it does change its shape a little bit with temperature. But we try to address these things in the initial design of the mirror before we even start making them. And that's the reason for the honeycomb sandwich mirrors. Right. The honeycomb structure gives you two things. One is that it makes it very stiff yet light. Mm-hmm. A honeycomb structure, it's like a two-dimensional version of an I-beam, mm-hmm. where you separate the mass. Our mirrors are about 3 feet thick, so most of the mass is at the bottom or the top. Mm-hmm. So those separated pieces provide the stiffness, just like the flanges of the I-beam provide mm-hmm. stiffness. And yet the mirror's 80% hollow. It's only got 1/5 of the mass of a solid mirror the same size. So it's got most of the stiffness, but not nearly as much mass as a solid mirror. So that makes it resistant to all the forces that try to bend it in the telescope. Mm-hmm. And you got one obvious thing you've got is gravity, because the mirror is being pointed in different directions. Right. So its own weight tries to distort it when you point it in a different direction. And of course, by having low weight, you minimize that. But the other big force you're dealing with is the wind. This is like a 28-foot sail on a yacht, and of course the telescope is wide open to winds. We want to be able to observe in winds up to about 20 miles per hour. Mm-hmm. So that's a heck of a force on the mirror, right. And it has to hold its shape to 100 nanometers mm-hmm. in the face of that. And again, you get it from the stiffness of the honeycomb.
And that wind, of course, is going to be doing some mechanical buffeting on the structure and so on. So it's a pretty ugly vibration environment, I would imagine, on a big telescope.
Right. Well, fortunately, it's other people who have to deal with the buffeting of the telescope structure and keep the thing pointed straight mm-hmm. in the face of that wind. But they managed to do that. Telescopes are designed with that in mind.
And for the temperature stabilization, you sort of alluded to that. So, this is not a pristine lab situation. You're out there in the elements and the wind and the dust as well, and then the temperature variation. And how does the mirror react to those day to night variations, and what does that do to images?
Okay, so that's another thing that's designed into these mirrors from the start. It's certainly an issue for two reasons. One is if the glass has temperature gradients, if one side's warmer than the other, then it'll expand more in the warm parts, and that'll distort the surface and therefore distort the images. So that's one thing that we need to minimize. And the other is that even if the glass is perfectly uniform temperature, well, the outside air is changing, generally cooling through the night. And as soon as it gets more than about a 1/4 degree C cooler than the glass temperature, you get turbulence sort of boiling off the surface of the mirror. It's the same thing you can see when you look across a hot highway or the roof of a black car in the summer. But what you see with your eyes is hundreds of times worse than what can be tolerated in a telescope. Right. So these tiny temperature differences are serious.
And they are tiny because the temperature day to night is varying by dozens of times that amount.
Yeah, that's right. So it means that as the temperature is changing through the night, the mirror temperature has to change with it. And it can't lag behind more than about 45 minutes. If you get more than 45 minutes behind, then you're going to be more than a 1/4 degree C behind in typical conditions. So again, that's part of the reason for the honeycomb design. The thickest section of glass in one of these mirrors is 28 millimeters. That's the front face sheet. And because it's so thin, it can track the changing air temperature with a lag of less than 45 minutes. And it can also be controlled so that the temperature of the mirror is uniform to better than a 1/4 degree also. So that gives you the other thing. It keeps the mirror the right shape. And those things, that can be done with thicker pieces of glass. Even at a few inches thick, you just can't get the heat out of the center, out of the middle of the section of glass fast enough to keep up with the changing air temperature.
Right.
That's exactly what sets the 28 millimeter face sheet thickness. And then all the rest of the mechanical dimensions follow from that.
Right. And this is the proof of the pudding is in the eating, and of course you do have big mirrors on telescopes north and south, so this has all been verified. But what's the limit on scaling this up? I mean, what the biggest mirrors you've made are how big?
8.4 meters, the biggest
and that's
in the world.
Biggest oven, right? But the technique in principle could go larger, right?
It could. You just run into practical engineering details that make it not worthwhile to go larger, and there are better ways to build bigger telescopes. Mirrors grew sort of, in fits and starts, but more or less steadily up to about 8.4 meters. And I don't think I'll ever see a larger mirror.
Right.
And, there may be no reason for a larger mirror for centuries.
GMT with its flower petals is sort of a typical way you go to the next level.
That's exactly what you do, and it's what everybody's doing to make the next generation telescopes. Put multiple mirrors together, and the engineering details of controlling a number of mirrors are easier to solve than the details of making a single big mirror and transporting it to the telescope.
Right.
Certainly transport is a big part of it, and it sets kind of a threshold at around 8 or 9 meters, because at that size we can carry the mirrors on the interstate highways as a wide load, taking 2 lanes with a police escort.
Right.
Much bigger than that, once you put a box around it, you wouldn't be able to take it on the interstate.
You couldn't get under the bridges or anything, presumably. Yeah.
Right, yeah.
And it's too heavy to fly to helicopter lift.
That's probably not impossible. The biggest mirror that's been transported by air so far is a 3.6 meter
Oh, okay.
mirror, which is in a telescope in Hawaii now, an Air Force telescope.
Mm-hmm.
And that was transported by airplane,
Right.
cargo plane. Yeah, so it can probably be done, but it just, I don't think anybody wants to be the first one to try it.
Right.
And it's going to be more expensive. And the bottom line is that you can make fantastic big telescopes and no doubt eventually achieve the diffraction limit of the telescope diameter by combining mirrors.
Now, of course, you didn't gloss it over, but you didn't mention the extra degree of difficulty in something like the GMT, where you've got all these off-axis optical elements, and your spinning is starting with symmetry, so that must be a challenge.
It is. I mean, it's far and away the biggest challenge I've ever faced. We just, for the first 18, 20 years of my time here, we just made bigger mirrors.
Mm-hmm.
And there were always challenges, but it was nothing like what we ran into with the GMT. Because it's designed with seven mirrors, 6 surrounding a central one, those outer 6 have a very strange shape compared to anything that we've made, compared to anything that anyone has made. So you can think on top of the standard shape of a mirror, kind of like a salad bowl, add a Pringles potato chip or a saddle shape that goes up and down by 14 millimeters as you go around the mirror.
Wow.
And that makes it very hard because you have to create this 14 millimeters of asphericity, as we call it, to an accuracy of a few tens of nanometers.
Mm-hmm. Yeah,
So,
wow. So that's like the most perfect Pringle ever made.
Yeah, that's
Yeah.
right.
Now, I'm sure, without giving away a state secret, I'm sure there have been white knuckle moments in your job. What are the moments or times when, it's been nerve-wracking?
Yeah, well, I would say every time we're machining a mirror, I'm a bit nervous about that, and I want to get through that as soon as possible.
Because that's the largest risk of fracturing, and
that's when things are happening fast. I mean, you're taking off cubic inches of glass per minute.
Wow.
And if anything goes wrong in that process, you can do a lot of damage very fast. Once you're into the lapping processes, where you got this tool resting on the surface, it's pretty benign. Things can go wrong that'll change the shape of the mirror, but it's harder to break a mirror there. But in machining, things are happening so fast that a mistake can have really serious consequences. We've had, everybody has had little mistakes.
Right.
And we've had a couple of potentially serious ones. One was in casting a mirror, one was in machining a mirror. But in both cases, we're able to recover from it and wind up with a mirror that's as good as perfect.
So we said it's experiential in the sense there's no book on this. So is there going to be a book? Are you or Roger going to write a book about how to do this for a future generation?
I doubt it. Boy, to try to... I think to write a book, you have to feel like you've got a systematic explanation for a lot of things. And unfortunately, there are large areas of this where there's not a systematic understanding. We're doing things the way they've been done for generations, sometimes for centuries, going back to Isaac Newton. And as much as I want to understand things on a physical basis and try to do experiments to illuminate what's going on, that there's too much that is still in the nature of black art.
So a way of looking at it, sort of like, of course you have models and you're doing that kind of work, but sometimes they don't. Sometimes the models don't help you, or you're in a regime where they're not very useful.
Sometimes the models are just I don't know, they're like the epicycles. They sort of explain what happens, but nobody thinks they're a microscopic explanation of it, a fundamental explanation. They give you good rules of thumb for proceeding.
Right. And it's sort of like you're dealing with classic multi-scale phenomena. You have, a huge mechanical object, and which is subject to stresses on all these different scales. You're working on it on different scales simultaneously, and that's probably just very hard to make a physical model that's meaningful.
Yeah, it's hard. I mean, I'm not saying it's impossible. I'm sure it could be done, and people will gradually learn more about how things work fundamentally.
You mentioned briefly the business of what happens after it leaves the mirror lab. I mean, that must be fun. Have you accompanied any of the big mirrors to their final destinations?
The only one I've worked on at all at the telescope is the MMT, and the only other one I've seen at the telescope is the LBT. Those mirrors, I haven't managed to twist my career into a direction where I can do anything at the telescopes yet.
And another little piece of this that some people are aware of is the talk about what it is that makes a mirror, and also it seems to me that older telescopes back in the last century, they used to take them out of their cells and illuminize them and so on, and it seems like nobody really these mirrors are too valuable and delicate and fragile to move around every few years, so it seems like they just stay there. They're too big.
They're just too big, right.
So how does the mirror part work?
Yeah, that's right. It's ironic. We don't technically produce a mirror. We just produce a piece of glass, and it becomes a mirror at the telescope. As you were saying, this used to be done in shops and in certain places around the country, but now every big telescope has its own aluminizing chamber. It's a vacuum deposition of aluminum onto the mirror, and so you need a big piece of equipment, a big bell jar that creates a vacuum, and it's easier to build that bell jar at the telescope and either take it right into the telescope and put it on the mirror, or just move the telescope over into a different building on the site. But nobody wants to be transporting big mirrors over hundreds of kilometers to the nearest coating chamber now.
Right.
Yeah.
So that creates an interesting mental image with the GMT. That just the hardware to do the re-illuminizing or illuminizing is quite impressive.
Right. So with all of our mirrors, the steel cell that holds the mirror in the telescope is designed to be the bottom half of the vacuum chamber.
Okay.
And then there's a separate piece, which is the bell jar, and that has the aluminum filaments scattered all over its ceiling, distributed so you get a uniform layer of aluminum on the mirror. So I think with GMT, the mirrors will go into a separate building to be aluminized. And that's something that'll have to be done every couple of years, and it'll take a mirror out of action for several weeks at least to clean off the old coating and get the new coating on. So partly for that reason, GMT will have one spare mirror, and whenever one comes out, another one goes in immediately the same day. I believe they're planning to do this without any loss of observing time. And then after this one's illuminized, it goes in a different place in the telescope. Of course, this only works because the 6 outer mirrors are identical.
Right.
They're interchangeable. And only the center one is unique. And when that has to be illuminized every couple of years, you'll just do without it for a few weeks. But still, you've got 6/7 of the collecting area and almost the full resolving power of the telescope.
And I guess it's an obvious question, but since you're talking about glass as the best material for the mirrors, I mean, aluminum is still the best surface coating for getting a reflective surface. There's nothing better. I mean, you could afford to use something more rare and expensive than aluminum, I guess.
Right, yeah, so people do for specialized telescopes, but my understanding is that for a multi-purpose telescope that's going to observe in the visible and infrared. Aluminum is the best compromise.
Okay.
And giving you, it gives you close to 90% reflection in the visible at least.
So what's next? I mean, the order book of the Mirror Lab is full for what, years now? How many years?
Well, I think we got a pretty firm commitment now through the 4th GMT mirror, and we're optimistic that that's going to extend through 8, including the spare mirror.
The spare, right?
Right. So yeah, that does that probably keeps us busy for another decade. It's a more secure situation than I've had most of the time here. I mean, we've always been terribly busy. We can't keep up, but there have been many times where we didn't know whether we'd have anything to do in 2 years.
Right.
And that's been going on for 26 years.
Wow.
And it certainly got a lot more solid with the GMT project.
And of course, it's the same, highly skilled and trained at this point set of people. So it's not. You could imagine parallelizing it, where if you could possibly do casting and polishing in parallel. But it's really the same people.
Oh no, but we are. I mean, we are doing these different operations in parallel. We're usually working on 3 mirrors at a time. So right now we're polishing one, which is the LSST mirror. We're machining the 2nd GMT mirror. We're building the mold to cast the 3rd GMT mirror.
Okay.
So I mean that's the only way we can get these things out on a
quick enough,
on an acceptable time scale. We can now, with this 3-station simultaneous production, we can finish a mirror about every 18 months, and we hope to get that down to 12 months before we get to the end of the GMTQ. And certainly the telescope project wants to have them on that rate.
Right.
Yeah.
Okay, cool. Well, I have one more question. I mean, assuming the GMT partners, didn't mind or could be persuaded, if I was going to come up to you with a blank check and say, look, I really need an 8.4 meter mirror. What am I looking at here?
Oh.
What's the damage for the whole deal, through the polishing and everything, just ready to roll?
Right. Okay. Well, so if it doesn't require a lot of new design, similar to something we've done before, you're probably looking at $15 to $20 million.
Wow. Okay, that's quite a steal. I'll have to think about that.
That's right.
Okay.
Sell a lot of books, Chris.
Yeah. Thanks, buddy.
Okay, great.